Hello there, welcome to the fifth section. We're almost at the end of the unit. I might have lied to you in the last video. This one might actually be shorter than last one. I said last one was going to be the shortest. This one might be actually shorter. We'll find out depending on how fast we go. So the purposes for this, we want to understand efficiency and we want to solve some problems involving efficiency. So in order to understand efficiency, you need to understand that efficiency is a measure of how much of the energy you put into a machine actually gets used. You can see some simple machines here in the picture. This is a physics understanding of machines, not a normal kind of idea with machines. So a wedge or a lever or a pulley, these don't seem like machines, but from a physics standpoint, we're going to use those as machines. So machines allow us to use less force over a longer distance to do the same amount of work. So it's causing it to be easier for us by making the force less for us over a bigger distance. And you'll see in the example how that comes into play. According to the second law of thermodynamics, which you don't need to know right now, but this is a very common law, you are always going to lose energy whenever work is done. You're going to convert it into heat. That's the law of thermodynamics, or the second law. So your work into the system, the amount of work you put in, is going to be less than what you get out. The work in being the total energy you put into the machine, the work out is what actually gets used up. So what actually gets used in your machine should be less than what you put in. So the equation for this is efficiency equals work out over work in times 100, or power out over power in times 100. Either one of these will work. It'll give you the same efficiency. There's no units for efficiency since it's work over work. Units cancel, or power over power, and those cancel. So here's our example. We've got a lever that's used to lift a 1.5 kg comm slug, 15 centimeters. To do this, Jorgen must apply a force of 5 newtons to the end of the lever, which displaces 85 centimeters, the long end. We want to find the efficiency. So I drew a diagram to kind of understand what's happening here. So here's our lever with a comm slug at the end. Jorgen's going to apply a force of 5 newtons down, displacing the whole lever, so the comm slug goes up. The force that Jorgen is applying is over 85 centimeters, and the comm slug goes up 15. So this is the diagram to show what's happening here. To get work in, we're going to use force times distance, since we're given the force and the distance, so it makes sense to do that. Don't forget to convert your centimeters into meters. So this is the work in. Work out is the comm slug getting moved upwards. So it's a change in potential energy, which is mg delta h. Again, don't forget to convert centimeters into meters. And here's the joules. Now, the confusing part is trying to figure out what is the input and what is the output. Your input, first of all, must always be bigger than your output. And you can also imagine what causes what. Does the force pushing down cause the comm slug to go up? Or is the comm slug moving up, which causes Jorgen to push? So what causes this motion is going to be your input, and what results is your output. So efficiency is work out over work in times 100. We're given those values. So this whole system is 51.9% efficient. So 51.9% of the work put into the system gets actually converted into the output. So there's the quick and efficient efficiency set of notes. Okay, this one we are moving to Indiana Jones, another favorite of mine, although not this movie. This one's not my favorite. First three definitely way better. This one, Indiana Jones is in a village that's by a nuclear weapons testing site, and watch what happens. Okay, there you go. What do you think happened wrong in this one? I think it's pretty obvious, but of course I would. I'm a physics teacher. So, taking a look at this, he decides that in order to survive a nuclear bomb, he's going to go into a fridge. And that's just ridiculous. Take a look at this fridge. Do you see any padding in that fridge? You should know this by now. It's the same with the Iron Man clip from a while ago. There's no padding. So as he's getting launched into the air with this explosion, he's going to bang into the ground. Yep, that's going to hurt. That one too. All of this bouncing is going to hurt. So yeah, he's going to be taking all those forces inside that fridge because there's no padding. That's not going to feel good. And then, if that didn't kill him, as soon as he opens that door, it's the radiation that'll get to him, because it hasn't dissipated in 2 seconds after it went off. So yeah, both of those are ways that unfortunately we would not have a rest of the movie for this one, because he's not going to survive that.